Today we're going to explain at a high level what Intel SGX is doing. We talk about its memory organization and also page swapping. So a specific, we talked about page swapping before, and we talk about how SGX is doing that in more detail. Now next week we're going to explain the Intel SGX enclave lifecycle, like how do you create this specific secure container, what are the steps that are being done in that, in what order. And we're also going to explain sort of what is the current status of Intel SGX considering its security. So what can it do, what can it not do, what is the reality around it, and so forth, and that will be a good discussion, I hope. After that, we'll be talking about how remote attestation is working. In order to do so, we'll also give a little bit of background in some of the crypto primitives that are being used for that. And then the week after that, well, we have a quiz and all that kind of stuff, but say the next lecture after that, we will have a lecture in which we specifically focus on the interface to memory in regards to encryption and integrity and freshness checking. How does Intel do that? How was it done before? What's the difference, and so forth. Okay, but let's continue with an overview, which we're going to do now. So first of all, a quick introduction. We already talked about it in many ways. So if you think about why compute devices are not trustworthy, it's simply because if you think about these privilege levels and you look at the OS, then it has access to the application, but you do not want the application to necessarily go through here to get high privileges. So you want to have some kind of a wall here. That is what you would love to see. Unfortunately, an application can be exploited to get access to this higher ring and then can launch attacks. So, so we want to make sure that that does not happen, but unfortunately, at the current state of affairs is malicious app with bad code can somehow get a privilege escalation, then is able to actually get into other applications as well. So that's what's happening now. The privileged code is now malicious, right, because you have gotten a footprint. And you can start to understand what this other application that you should know nothing about, what it is doing, and you get information about it. So applications are typically not protected from privileged code attacks. So what's the attack surface today? Well, in current systems, a large code base constitutes of all these three items: application code, OS code, virtual machine manager code, and so forth. And those are many, many, many lines of code. Now, what is SGX going to do for us? It allows applications to defend its own secrets. And how is it doing that? We are going to trust just a little bit of hardware and say a sensitive application module that is executed in a container, but we do not need to trust an operating system. So we deviate from this attack surface now that we see today by allowing the operating system to be untrusted. So currently we have all these millions lines of code, and there will be exploitable bugs. All right, so SGX enclaves allows us to have a reduced attack surface. And what is the whole idea? The whole idea is really that we just have a piece of hardware that we need to trust. So if you attack that, then obviously you can break in. And we also need to trust the application code or modules that are being executed in these enclaves. So we have isolation principles that surround the build-up of these SGX enclaves. But besides that, we still need to make sure that the modules that are executing in those enclaves are trusted. And then you can have a true trust guarantee. Okay, but from the SGX Intel perspective, the supplier of the security environment, we are interested in how that isolation takes place and that there's no other kinds of strange mechanisms outside application module vulnerabilities that you may have to infiltrate into that secure enclave and container. All right, so let's see how that works. So first of all, what is an enclave, right? That's the key concept behind SGX. It's a protected environment that contains the code and data of a security-sensitive computation. And we'll go through this in much more detail now. Also note that there can be many enclaves in the system at a time, and also a single enclave can have many threads that it executes, by the way. So, you know, if you're executing application code in general, right, you have many threads that execute in parallel. And within an enclave, you can do the same. All right. So you also need to supply for context switching, for example, between enclaves and so on. So you need to enter an enclave and exit an enclave. And how do you do that? Now, that has to do with the SGX enclave lifecycle, and that we'll talk about on Monday. Now we give a lot of background on the details or mechanisms that SGX applies at a higher level. So what do we want? We want isolation. Each enclave's environment is isolated from the untrusted software outside the enclave as well as from other enclaves. And we want attestation. So what does that mean? Well, I may be a remote user of the SGX environment, and as a remote user, I want to attest that my application software is running in that particular environment, that particular machine, with that particular SGX Intel configuration effectively, because that CPU has its own private key that it can use for signing, say, what it does. And I can verify with a public key then that is known to relate to that trusted environment by the manufacturer. So I trust the manufacturer for that. And I can then effectively conclude through that signature scheme, that is a crypto primitive that we'll talk about later. Effectively, I can now attest to the fact that my software is running at that remote computing environment that actually has an SGX Intel processor, etc., etc. So we want to protect the privacy and integrity of the computation. Privacy means it's confidential, and there's no information that leaks. Integrity means actually here, I want to make sure that the computation uses the right data for the computation, right? So if I'm going to replay data with older data, we talked about it a little bit last time, well, the computation is not correct. I may trust that the actual code is being executing. I still have to fetch the instructions from memory, by the way, so I need to make sure that I fetch the right instructions, but I also need to make sure I fetch the right data. So all of that is authentic and fresh. So I want to make sure that that all happens.
That is the DRAM freshness, right?
That's the DRAM freshness, and of course also when you do page swapping, you can extend it to external memory freshness in its larger concept.
And the software, so each software, for example, is encrusted, and within that software there is this enclave, right, which is trusted.
Yes, correct.
Can one software have multiple enclaves inside it?
Yeah, so one application software can effectively, well, enter an enclave, create an enclave, and an enclave later exits, right, to give back the information. But application software should be able to, on its own, have multiple threads, and each thread could potentially go through a sequential processing where at some point you have an enclave being created and exited. And within an enclave, you can have multiple threads within that enclave as well. So yes, you could have multiple enclaves. And also, you can have multiple applications that should be isolated from one another to begin with, obviously, but we assume the application code is untrusted, except for that what is running in those enclaves. But you can have from different applications, you can have secure enclaves too. And they all run, obviously the CPU runs only one thing one time. So you do context switching to do resource sharing, but you effectively may work with all these enclaves at the same time, and they all need to be present somehow in the memory, in the system memory, in a way that provides this privacy and integrity. If you think about an enclave being exited and entered and you know, context switched and so forth, and at the end you would like to have that the computation coming out in a proper way. That's sort of what we will aim for. So general computational paradigm. So here it is. So we have an application. So the app starts from an untrusted part. That's important to understand, and wants to call something security critical. All right. So you want to do something sensitive. So you create an enclave. We just talked about that, using some special instructions, which we talk about next lecture. The enclave is placed in an entrusted memory now, that is isolated from anything else, and this includes the code and the data being used by that enclave. All right?
Who manages the enclave?
Sorry?
Who manages the enclave?
So we'll get to that, who is managing the enclave. So we'll go through all of what's going on. The hardware is managing the enclaves, obviously. So we'll go through all these steps now.
Is there any kind of overhead for putting your code in an enclave?
Well, you do have, entering an enclave and setting it up does cause some overhead, but it's, you know, you may think it's amortized away if you just enter it and the critical code is running for a while. So it may not be a severe penalty.
And context switching also has its own overhead.
Yeah, of course, because you need to take care. Not only that, we will see later on at the end, even like swapping pages out of the enclave, that costs a bunch of overhead too. That's why you need to make sure that the hardware is done in such a way that it's pipelined as best as it can, right? And to do what hardware is good at, and let's not have the performance overhead too much. And that includes all kinds of checks that need to be done that you would like not, that you want the hardware to take care of in an efficient way. No, it's not an easy task, obviously, to make this all work from a performance perspective. So where were we? So, well, okay, so then it calls a function to enter that enclave. So now you go into the enclave, you execute, and effectively, so even if a privileged software like an operating system is now trying to access that enclave, this access will be denied by the hardware. That's important. So the required functionality has been achieved by executing the secure code once it returns, and then you continue. So this is effectively what's going to happen at a very high level. Now, these are slides from Kamran. I did not, it's on the first slide, but he makes beautiful pictures and he doesn't even change this. It's just beautiful. So a high level overview. This is a really nice overview picture. So what are we going to talk about? We're going to talk about the programming environment, access control, so isolation, attestation at a very rough high level. We will get into much more detail next week. And memory snooping protection. So here we are. So the trusted execution environment, is embedded in a process. So application is built with code and application data, which is security critical, and this is put inside an enclave. Here it is. So you create a secure enclave. There it comes. And what we have here is a view of the virtual address space, right? And we will later talk about the translation to the physical, how it looks at the physical layout in memory. So it's a later point. All right, so the process creates a secure enclave. So what is needed for that? So first of all, so what kind of features does that give you? That's what I like to talk about now. So first of all, I said it contains the code and the data. You want to provide confidentiality, integrity, and freshness. And you would also like to make sure that you have controlled entry points. You cannot just willy-nilly jump into the enclave's code. You need to go through a very specific procedure.
It is written the process creates a secure enclave. Which process?
Yeah, so your application code is actually having e-creation, meaning that an enclave is being created. We will talk about it next week. And then this enclave comes into being. Now, notice, by the way, there are probably also other options that I'm now thinking about on top of my head, but like a remote user may also want to maybe create, give material that will create a secure enclave. So for example, the code itself may not be secure. It's secure in its execution, but may not be private in its execution. It's okay to say, my code is doing some machine learning effort, I'm just saying something, like say face recognition, but it's not allowed to reveal what face it's recognizing. So you know it's a face recognition algorithm. What data is supplied? Well, I'm not going to supply data that's not encrypted, right? But within this code, I may be able to decrypt it, but how does it get to know the key? So it's probably a little bit more complex how you deal with a secure enclave from the perspective of untrusted application code. But if I have a remote user that I trust, remote user can possibly set up a channel through which is now authentic and secure with a secure enclave, through which you can actually give the key that is needed to decrypt, say, the data that you have given it in the first place to do some work. Or you can stream in data, you can do all kinds of things, obviously. But I try to cook up an example to explain to you that there are several steps involved to understand how the untrust to trust boundary gets crossed into some extent. It never gets truly crossed, right? You always need to have a root of trust somewhere based on keys and so forth, and someone needs to give that to that enclave. All right, that's how far I get here. So now, so controlled entry points, very important. So I need to jump to a specific point and start executing the code from there, and I cannot jump to an arbitrary point. That's very important. So there's a specific procedure to follow, and well, then there's some more things that are supported, more features. It supports multiple threads. That makes total sense, and an enclave has actually full access to the application memory, like also all the other data, obviously, that's being used by the application can be accessed. It's in trusted environment anyway, right? But you can still access all of that as well and use it in your computation. It makes total sense. Again, it's the idea that the trusted environment can access everything, while the untrusted environment cannot access what the trusted environment specifically has access to. So even though the privilege levels of the untrusted application code and enclave are the same with respect to the computational stack hierarchy, right? If you think about trust levels, you still have that isolation boundary set up in a way that feels like different privilege levels when it comes to security features. That's maybe a little bit confusing, but you can think it through. What we have here is a general architectural diagram. So the basic hardware platform on the bottom there has some special structures that you need to trust. That's the hardware attack surface, if you will. It's the EPC that we'll talk about and the EPCM. Now, part of SGX is executed by the privilege environment, which is part of the operating system. So for example, page tables and so on. But in order to make sure that that works properly, you need to verify that it is working properly. So some checks need to be in place in the hardware. We talk about it also later on. So most of these functions that are on the right we'll not discuss, but we'll definitely discuss the first bunch on top next week. That's related to the life cycle. The e-reporting is to do with remote attestation, by the way, and there's some other things that we will glance over. All right, so we'll discuss. We'll discuss some of these instructions. I think most of them. But so they're related to entering, exiting, executing code inside the enclave, page swapping, and so forth. All right, SGX access control at a very high level again. How is isolation provided? How does that work? So if you look at this particular part of the picture, this is totally traditional. Remember when we talked about address translation, you start with a logical address, here it's called linear address, virtual address, right? And we want to translate that by looking at several pages, and then in the end we get a physical address, and that we can use to actually access the memory. The hardware is in charge of now making that a reality, right? So is that physical address truly allowed to be accessed is now the question, and this is where the access control comes in. So later we will talk on much more details, and that will only be in about 3 lectures, I believe, when we talk about a decision tree that needs to be followed in order to make sure that the data that's being read from the untrusted system memory can be trusted and can be used by that particular application or enclave, depending. So here we are. First of all, is it, okay, good. So access is made by a program in enclave mode or not. You want to verify that. If not, then the physical address may land in some privileged DRAM region, and we call that EPC. It stands for Enclave Page Cache. So this can only be accessed by enclaves. So if that is indeed true, the address in EPC, then that is not allowed. Because it's not true that the enclave was accessing this, but it wants to land in enclave protected memory. So if that is true, you need to do an abort. Now, if not on the other hand, in other words, we have just an ordinary application, an ordinary mode, it's not an enclave, accessing ordinary memory in DRAM, then in that particular case we allow memory access. All right. Now, if it comes from the enclave mode, so that's the yes part over there, then if the address is also in EPC, if that is true, if that's a yes, oh wow, what happened here? So did it fall automatically?
No, it's fine.
Okay, all right. Okay, cool. So anyway, so what I wanted to say here, if the address is also an EPC, you still need to do a bunch of checks. Why? For example, you need to verify that the same enclave that created that particular physical memory that is stored at that address is now also accessing that, right? It could be another enclave that tries to access this particular enclave's memory. That's not good. So you have a bunch of checks. We'll go through the details later on. So if that passes, then you're happy, you allow memory access. Now, if that's not the case, then obviously there's a fault. And that's what's indicated here. So if you do enclave access, but the address is not in the EPC part, then you have a problem. If the checks that we talked about do not pass, you have a problem as well. All right, so the EPCM verifies that the enclave owns this address. It verifies that the same mapping from virtual to physical address is being used as what was used the last time, because that may change. For a certain virtual address, we may have several versions of the physical address, because we may swap things out and back, and also that is out of EPC memory and back and forth. So we could do that, and that means that you need to make sure that its page table is really using the most fresh information. So we need to have extra checks. So that's another example of what we do here. All right. So let's talk about now. So we had a very high level overview of isolation to some extent. Let's go a little bit and talk about attestation, even though we'll go in much more detail later on. So the question is, do you really execute the code in the right environment if a client with a remote platform is going to execute some stuff. So how do I know that that client application runs the proper stuff? So you would like this to be endorsed by Intel and trusted. So say I have a certain critical code, then I want to build an enclave, put my code in it, and the data required in it. And now I would like to measure that. What does that mean? It simply means that I take all of the pages, all of the stuff that builds up that enclave, and I'm going to hash it one by one and add it together. So create just a hash of that thing, and that hash can, for example, be signed by the SGX Intel, the Intel SGX secret key that is part of that hardware. So now I can verify later on that that particular measurement, that hash, is actually related to the output to what that enclave generates. So what I want to say, you create a measurement of that whole thing, a hash of the whole thing. You store that hash in the enclave itself as some metadata. That's what will happen. Later on, so it's probably the next bullet, I want to, as a remote platform, request a report on the output of the enclave. So it has generated some output. What do? I'm going to hardware sign, that's this particular thing over here, a hardware signed blob that includes the enclave identity information. So it's not just the output that is being signed, it's also that measurement of the enclave. So now I can verify the hash on my own and verify that, yeah, that's the right code and the right data that was being used initially to do this kind of stuff. I may have interacted with this enclave also and give it information back and forth, but I know that the start of that enclave was the way I anticipated it to begin with. So I can verify that. So now I know that the output that comes out of the enclave can be trusted, because I also trust the signature mechanism that depends on a secret key.